Welcome, dear learners. We are continuing Unit 3, Introduction to Nanomaterials. In this module, we are discussing classification of nanostructures. The contents of this module are classification of nanomaterials based on electron confinement, zero-dimensional, one-dimensional, two-dimensional and three-dimensional nanomaterials or nanostructured materials, quantum well, quantum wire and quantum dot, quantum confinement effect, degrees of freedom and degrees of confinement, and finally several MCQs associated with the concept in this chapter. First of all, classification of nanomaterials based on electron confinement. This classification was introduced by R.W. Siegel, Richard W. Siegel. He classified nanomaterials based on dimension. That is, the classification is based on the number of dimensions which are not confined to the nano range. We all familiar with the three spatial dimensions x, y and z. This is the x coordinate, this represents y coordinate, this represents z coordinate. These are three dimensions normally. Whenever we are taking a material and how many of its dimension are confined to the nano range. In certain cases, all three dimensions are confined to the nano range. In some other case, it may be 1. In some other case, it may be 2, etc. So, based on the dimensions which are not confined to the nano range. This is very important, which are not confined to the nano range. We can classify nanomaterials. Such a kind of classification is known as Siegel's classification or classification based on number of dimension, etc. We can enter into more details of such a classification. First of all, there will be 4 types of nanomaterials based on the classification by dimension. Strictly speaking, the classification is based on the fact that the number of dimensions which are not confined to the nano range. So, the 4 types of nanomaterials based on this classification are: first one, zero-dimensional nanomaterial; second one, one-dimensional; two-dimensional; and finally, three-dimensional nanostructures. We can enter into the more details of each and every subtitles. First of all, zero-dimensional nanomaterials. What are zero-dimensional nanomaterials? Zero-dimensional nanomaterials are such materials wherein all dimensions are measured within the nanoscale. That is, among 3 spatial directions x, y and z, all the dimensions along x direction, that is along y direction and along z direction, all are confined, all are restricted, all are in the nanoscale. In the nanoscale means in the range of 100 nanometer. So, whenever you are taking a zero-dimensional nanomaterial, its x-axis is in the range of 100 nanometer. Similarly, y also and z. So, all 3 dimensions are in the nanoscale range. That means no dimension is outside nano. Hence the name zero-dimensional. So, the number 0 represents the fact that no dimensions are outside the nanoscale. All dimensions are inside the nanoscale. That is the meaning of the term zero dimensional. Now, no dimensions are larger than 100 nanometer, hence the name zero dimensional. The most common representation of or most common examples of zero dimensional nanomaterials are nanoparticles. Metal nanoparticle like gold, silver, platinum, etc. Quantum dots, etc. are nice examples. We can enter into further details of zero dimensional materials in coming slides. Now, the common features of zero dimensional nanomaterial. The zero dimensional nanoparticle or zero dimensional nanomaterials can be amorphous or crystalline. You are familiar with amorphous material. They will not have any sharp melting point, regular crystal planes, etc. And opposite to that, crystalline materials have a sharp melting point, regular crystal planes, arrangement, etc. Isotropy, anisotropy, etc. are some differences concerning amorphous and crystalline materials that you have learned in your school classes. And this zero dimensional material may be amorphous or crystalline, that is the first peculiarity. And the second peculiarity, it may be singly crystalline or polycrystalline. Next characteristic feature is the zero dimensional nanomaterial may comprise of single or multi-chemical elements. And next feature is that zero dimensional nanomaterial exhibit various shapes and forms. It may be spherical, it may be in the form of rod, it may be dispersed arrangement. Yes, the various kind of shapes is possible for a zero dimensional nanomaterial. And the next characteristic feature is it exists individually or incorporated in a matrix or maybe metallic or maybe ceramic or maybe polymeric. This implies that the zero dimensional nanomaterial can be constructed from metals, can be prepared from ceramics, can be prepared from different kind of polymers, etc. They may have sometimes individual existence, or sometimes we need to stabilize them. In order to stabilize them, we have to put it in some solid matrix, etc. That is the implication of this statement. So, there are so many features associated with the zero dimensional nanomaterials. Now, we are focusing on next kind of nanomaterial, that is one-dimensional nanomaterial. So, I already mentioned the fact that the Siegel's classification is based on number of dimensions which are not in the nano range or which are outside the nano range. How many dimensions are outside the nano range? So, simply keep in mind the fact that the number shown here represents number of dimensions outside the nanoscale. So, for one-dimensional nanomaterial, only one dimension is outside the nanoscale. For example, in x, y and z directions, if x direction size is outside the nano and y and z will be inside the nano size, you can call it as one-dimensional nanomaterial. The definition is like this. If one dimension is outside the nano, you can call it as one-dimensional nanomaterial, and this leads to needle-shaped nanomaterial. Then the question arises, why the needle shape? So, in the needle, the length is very high, but its breadth and thickness, etc. very low. Two dimensions are very small. The dimension length is very high. So, one dimension is outside the nano. That is why these kind of nanomaterials have needle or thread-like shape. Now, 1D nanomaterials include so many examples like nanotubes. You heard something about the carbon nanotubes. In our coming modules, there will be discussion on carbon nanotubes. Then we can study more details. Then nano rods are there, nano wires are there. See, in all these arrangements, it is very well clear that there is a long arrangement. There one dimension is very lengthy. That is, one dimension is outside nano. This is the representation of a carbon nanotube. This is a tubular arrangement. Its thickness, its breadth, etc. very small, but its length is very high. So one dimension is outside nano. So carbon nanotubes represents a nice example for one-dimensional nanomaterial. Now, the features, the characteristic features of such one-dimensional nanomaterial, these are the characteristic features. Again, as in the case of zero-dimensional nanomaterial, this only nanomaterial may be amorphous or crystalline. It can exist in two different forms, both the forms. It may be amorphous or it may be crystalline. Now the next feature, again it may be singly crystalline or polycrystalline. Another feature is it may have some impurities. In some other cases it may be pure. So it may be chemically pure or sometimes some impurities present, may be pure or impure. Next case, it is a standalone material or may be embedded within some other medium. This, what is the meaning of the last statement? It is simply like this. Sometimes this only nanomaterial can exist as stable entity without incorporation into some other materials. In some other cases, the nanomaterials may be unstable. In order to increase its stability, we are putting it into some other solid matrix, that is means embedding. So, these only nanomaterials may be standalone material or it can be embedded within other medium. Nanorods are nice examples for one-dimensional nanomaterials. What are nanorods? The nanorods may be synthesized from metals or semiconducting materials. As the name indicates, they are rod-shaped, lengthy nanomaterials. So, from this, it is clear that they are one-dimensional. And these nanorods have very high length. In nanoscience, the length to width ratio is termed as the aspect ratio. The aspect ratio of nanorod is in the range of 3 to 5. This is a pictorial representation. It's a transmission electron microscopy image of gold nanorods. Gold nanorods. These are the one-dimensional nanomaterial prepared from metallic gold. It appears to be rod-shaped. So, this is an example for one-dimensional nanomaterial. And from this image also it is clear that its length is 3 to 5 times of its width. So, aspect ratio is in the range of 3 to 5. Nanorods provide nice examples for one-dimensional nanomaterial. Now, we are entering into next classification based on dimension, two-dimensional nanomaterials. Before entering into the details, we have to keep something in our mind that this number 2 represents two dimensions are outside nano size. That is, only one dimension is inside the nano range. By keeping this, we can enter into definition to two-dimensional nanomaterials. Two-dimensional nanomaterials have two dimensions not confined to the nanoscale. Not confined to the nanoscale means not in the nanoscale. That means two dimensions are higher than nanoscale dimension. That is, only one dimension is in the nano, two dimensions are outside the nano. 2D nanomaterials exhibit plate-like shape. This moving picture represents a nano arrangement, a 2D nano material that is nothing but the graphene sheet. We can study more details about the graphene and other different carbon-based nanomaterials in coming modules. And two-dimensional nanomaterials include thin films, nanofilms, nano layers and nano coatings. So, they have a planar structure. So, for a planar structure or similar to a very thin sheet of paper, two dimensions are outside nano. Its thickness is very small. So, one dimension is inside nano and two dimensions are outside nano. Hence, the name 2D nanomaterial. We can enter into the features. More or less, the features are similar to previously discussed zero and one-dimensional. we can again move to the characteristic features. It may be amorphous or crystalline as in the previous two cases, made up of various chemical compositions, used as a single layer or act as a multi-layer. It may be exist in the form of single layer or it may be like a multiple layer. Suppose for example, we can take a single sheet of paper, you can take so many sheets of paper and arrange it as layers. So, it represents a multi-layer. In a similar way, 2D nanomaterials can be arranged in layers also, that is called multi-layered arrangement. It may be in the form of a single layer or it may be in the form of a multiple layer. Now, it can be deposited on a certain substrate. For you are familiar with some thin films. So, in thin film technology, we are depositing two-dimensional nanomaterials. Thin films are two-dimensional nanomaterials. Its thickness is very small. That thickness is only in the nano range. Its length, breadth, etc. are outside the nano range. So, definitely a thin film is a two-dimensional nanomaterial. Thin films are generally deposited on a solid substance. That is called a thin film deposition technique. So, thin films or 2D nanomaterials are generally deposited on a substrate. Now, more details about the thin films. A thin film is a layer of material ranging from fractions of a nanometer to micrometers in thickness. Its thickness may be sometimes increase up to micrometers. They are thick thin layers. Thin films created through a process called deposition. I already mentioned the fact that thin layers are generally, thin films are generally deposited on the surface of a solid substrate, and that technique is called thin film deposition or simply the deposition. Deposition is a thin film coating process. You can take a solid material like silicon carbide, etc., on the surface of which you can coat a thin film, a nano thin film. Thin films are very nice examples for two-dimensional nanomaterials. Now, the last category, three-dimensional nanomaterial. My question is, before entering into the details, my question to you is that, what this number 3 represents? What is the implication of the number 3? The number 3 represents the fact that all the 3 dimensions are outside a nano. Then one important question again appear in your mind. If all the 3 dimensions are outside a nano, how we can call it as a nanomaterial? Here there is the answer. Now see this definition carefully. These 3D nanomaterials are also known as bulk nanomaterials. So, by definition, what we learned about a nanomaterial? A nanomaterial is a material with at least one dimension in the nano range. But for 3D nanomaterial, all the dimensions are outside the nano range. Then how these two definitions will be synchronizing together? It's an important question. So, you take a nanomaterial. Suppose that individual nanomaterial is assembled together. Now, individually they are nanomaterials, but they assembled together. We will get a bulk nanomaterial. It is not a bulk material, it is a bulk nanomaterial. If you are considering the bulk nanomaterial, that is a group of nanomaterial, then for that entity, it is x direction, y direction and z direction. All the directions will be outside nano. Such a system is called bulk nanomaterial or 3-dimensional nanomaterial. Never get confused with the fact that 3D nanomaterial is not similar to a 3D bulk material. 3D nanomaterial is an assembly of small nanoparticles and lead to a structure overall in such a way that all dimensions are outside the nano. So, individually they are small nanoparticles, but assembled together to produce a big size with all dimensions outside a nanoscale. Hence the name assembled nanostructures or bulk nanostructures, etc. They are not bulk materials. Bulk nanomaterials, not bulk materials, bulk nanomaterials are not confined to nanoscale in any of its direction. Even though this is the fact, they are individually small nanoparticles. They are characterized by having 3 arbitrary dimensions, namely the x, y and z dimensions above 100 nanometer. This happens because of the assembling of the nanomaterials. They are still nanoparticles, but they assembled together. So, this is the difference between 3D nanomaterial and a 3D bulk material. 3D nanomaterials are composed of a multiple arrangement of nano-sized crystals. This thing is clear to you. Now, this bulk nanomaterial contain dispersion of nanoparticles, bundles of nanowires, nanotubes, as well as multi-nano layers. If there are a thin sheet or a thin film, enormous amount of thin film arranged together to get a multi-layer, then the size, then the height of the thin layer increases. After certain level, that dimension is also changed to bulk dimension. So, it can be considered as a 3D nanomaterial. Remember, this point is very significant. 3D nanomaterial is different from bulk material or 3D material. 3D nanomaterials are obtained by the assembling of individual nanoparticles. That individual nanoparticles may be nanoparticles as such, nanowires, nanotubes, or it consists of multi-layers. Another important area of today's discussion is about quantum well. Now, you are familiar with the classification of nanomaterials based on dimension. What is a two-dimensional nanomaterial? The number 2 represents 2 dimensions are outside nano. That is, 1 dimension is inside nano. If 1 dimension of a bulk material is reduced to the nano range, while the other 2 dimensions remains large, we will get a quantum well. So, it is very well clear that the quantum well are 2-dimensional nanomaterials. This is the representation of a quantum well. Here you can see only thickness is in nano range, and other 2 dimensions, length and breadth, are outside nano. So, this is example to a thin layer or a thin film or a thin sheet like that, or a graphene sheet, etc. All this belongs to the general category of a material that is nothing but quantum well. Next part is quantum wire. If 2 dimensions of a bulk material is reduced to nano range, while other one remains large, then we get a quantum wire. That is, quantum wires are general name given to 1D nanomaterial. But this quantum wire is theoretically different from nanorods. We previously learned about the nanorods, and for nanorods, the aspect ratio is between 3 to 5. But for a quantum wire, the length is again very high when compared to width. That is why length to width ratio or the aspect ratio is very high. It is in the range of 1000. What is meant by aspect ratio 1000? Aspect ratio 1000 means the length of the quantum wire is about 1000 times greater than its width. So, they are particles with very high length. So, this is the difference between quantum wire and a nanorod. Nanorod and quantum wire both are only nanomaterials, but quantum wires more specifically have a higher aspect ratio compared to nanorods. Now, the last category, that is quantum dots. Quantum dots are very important class of compounds in nanotechnology with several applications. We can enter into details of the quantum dot. If all 3 dimensions x, y and z of a bulk material is reduced to the nano range, x direction is reduced to nano, Y direction is reduced to nano, Z direction is reduced to nano. The material obtained is called zero-dimensional nanomaterial. Not all zero-dimensional materials belongs to quantum dots. These quantum dots are especially semiconductor-based nanomaterials. We can study more details about the physical properties, chemical properties, etc. of quantum dots in coming modules. Okay. So, quantum dots are simply zero-dimensional nanomaterials, but all zero-dimensional nanomaterials cannot be considered as quantum dots. So, we can say like this, quantum dots are special categories of zero-dimensional nanomaterials. There are different type of quantum dots based on their structure, etc. This picture represents a core shell type quantum dot. There is a core means the body, the entity present at the center, and there is a shell. These are the materials present outside. This is a pictorial representation of a core shell type quantum dot. Now, how a bulk material is converted to different nanostructures. This is about the concluding remark of the classification of the nanomaterial based on dimension. So, in the Siegel's classification of nanomaterials based on dimension, there will be a number like 0, 1, 2, 3, etc. That number represents number of dimensions which are outside nano, That point is very important. The number shown here is in 1D, 0D, 2D, etc. That number represents dimensions outside nano. Total there are 3 dimensions. Okay. Now we are discussing how a bulk material is converted to different nanostructures like 0D, 1D, 2D, etc. How these kind of nanomaterials are obtained from a bulk material, that is our discussion. This picture clearly depicts the transformation. Now look on to the left hand side. This side represents a bulk material. It is big such that X direction is outside nano, Y direction is outside nano, Z direction is also outside nano. So definitely this rectangular arrangement represents a bulk material. Now I take one axis, say this, namely the x-axis. This x-axis is reduced. That is, the x direction is reduced to the nano range. Only x direction is reduced to the nano range. See other 2 directions, the y and z directions are still large. That is, 2 dimensions are outside nano and only 1 dimension is inside nano. Since 2 dimensions are outside nano for this arrangement, you can call it as a 2D nanomaterial. Again, I am reducing one more dimension, say the Z direction. Then X direction and Z direction. 2 directions are reduced to nano. Direction or dimensions are reduced to nano. Only 1 dimension is outside nano. Hence, these type of materials are called 1D nanomaterial. And for the last arrangement, I reduce the remaining 1 direction again to nano. So, for this, X direction is nano, Y direction is nano, Z direction is also nano. So, all 3 dimensions are inside nano, no dimensions are outside nano. Since no dimensions are outside nano, I can call it as a 0-dimensional nanomaterial. So, this is 2-dimensional nanomaterial, 1-dimensional nanomaterial and a 0-dimensional nanomaterial. This 2 represents 2 dimensions are big. This 1 represents 1 dimension is big and 0 represents no dimensions are big. That is, all dimensions are inside nano. This is quantum well, quantum wire and quantum dot. So, this is the transformation of a bulk material to other types of nanomaterial. Now, this conversion, if you are taking a spherical shaped particle, again this depicts the transformation. This is a very big sphere like a football, volleyball, etc. like that. It is a bulk material. it is again pressed in one dimension, you will get two-dimensional nanomaterial, that is a quantum well. If you are again pressed in two directions, you will get a quantum wire. If you are pressing in all dimensions, you will get a small particle in all dimensions, that is zero-dimensional material, that is quantum dot. This is the transformation. So, it is very well clear that how a bulk material is transformed into different sized, different dimensions of nanomaterials. Now, this is a consolidation chart where you can see the dimensions and their examples. For 0D, all dimensions are inside the nanoscale. Examples are nanoparticles, quantum dots, etc. For 1D nanomaterial, two dimensions are at the nanoscale, one dimension at the macro scale. That means only one dimension is at the macro scale means at the bulk scale. Two dimensions are in the nanoscale. Total is 3 always. Nanotubes, nanorods, etc. are nice examples. Quantum wires are also good example. For a 2D material, one dimension at the nanoscale and two dimension at the bulk scale or macro scale. And examples are provided from nanofilms, nano layers, nano coatings, quantum well, etc. And the last category, the bulk nanomaterial. And for a bulk nanomaterial or a three-dimensional nanomaterial, no dimensions are at the nanoscale, all dimensions are at the macro scale. This is similar to a bulk material, but the difference is that these 3D nanomaterials are assembly of small nanomaterials. That fact is very important. Dispersion of nanoparticles, bundles of nanowires, etc. are examples for 3D nanomaterials. So, this is a consolidation chart of our discussion about zero-dimensional, one-dimensional, two-dimensional and three-dimensional nanostructures. Now, quantum confinement effect. The word confinement means a restriction. Electrons are the ultimate particles. Whenever you are restricting the mobility of the electron, there occur an effect that is called quantum confinement effect. The quantum confinement effect, the confinement means you are confining, you are restricting the motion of electrons in specific energy levels, and quantum denotes atomic realm of particles, hence the name quantum confinement. The quantum confinement effect is observed when size of the particle is too small to be compared with the wavelength of electron. That is, whenever you are reducing the particle size either in x direction, y direction or z direction or in all the directions, then the quantum confinement effect is reflected if and only if the size is reduced to such an extent in the range of wavelength of electron. You know, electron is a very small particle, its mass is very low, so it is associated with the high wavelength. Lambda is equal to h by mv. De Broglie relation is also familiar to you. So, there is a wavelength of an electron, and if the particle size is reduced in the range of the wavelength of the electron, then occur the quantum confinement effect. The quantum confinement effect describes electrons in terms of energy levels, potential wells, valence band, conduction band and electron energy band gap. So, the quantum confinement effect is reflected in the band gap, the energy difference between valence band and the conduction band, and this quantum confinement effect is reflected in many of the properties of the nanomaterials like quantum dots, quantum wires, etc. For quantum dots, there is a phenomena called size tunable emission. That is, whenever you are changing the size of the quantum dot, its color also changes. The change in color with the size is termed as size tunable emission, size tunable color. That is a direct consequence of the quantum confinement effect. This we can study in coming modules whenever we are discussing about the quantum dots, etc. This is simply a term, quantum confinement effect, which related to the confining of the motion of the electron, and it will be reflected only if the size of the particle is reduced to the size of the wavelength of the electron. Now, two important things to be noted here from our classification, that is degrees of freedom and degrees of confinement. Confinement means a restriction. Freedom means you are giving the size in bigger dimension. That is, you are increasing the size. So, degrees of freedom and degrees of confinement are two important aspects associated with our classification based on dimension. Degrees of freedom denotes the number of dimensions through which delocalization occurs. That means number of bulk dimensions, that is dimensions outside the nano. Degrees of confinement denotes the number of directions that are confined. That is degrees of confinement simply represents dimensions inside nano. Degrees of freedom represents number of directions outside nano. You know there are three spatial dimensions. So, degrees of freedom plus degrees of confinement equal to 3. For an only nanomaterial, how you can explain this? For an only nanomaterial, one dimension is outside nano. So, degrees of freedom is 1. In 2 dimensions, it is inside nano. So, degrees of confinement, it is equal to 2. 1 plus 2 is equal to 3. Hence, the relation degrees of freedom plus degrees of confinement equal to 3. So, simply you can remember like this. Degrees of freedom means number of dimensions outside nano. It is given by the number in the classification. In 1D nanomaterial, it is 1. In 2D nanomaterial, it is 2. So, degrees of confinement, it is the dimension inside the nano. That is obtained by subtracting degrees of freedom from 3. Because degrees of freedom plus degrees of confinement equal to 3. So, depending on dimensions of confinement, 3 kinds of nanostructures are known: quantum well, quantum wire and quantum dot. This we already discussed. And this is the consolidation chart of bulk material, quantum well, quantum wire, quantum dot, etc. based on DC and DF. DC represents degrees of confinement and DF represents degrees of freedom. So, for bulk material, degrees of confinement is 0. That is, the particle can have freedom along x, y and z direction. For quantum well, degrees of confinement is 1. Degrees of confinement is 1 means one direction is confined. 2 dimensions are not confined. So, it is a 2D nanomaterial. Similarly, you can see the case of quantum wire and quantum dot. Here, for remembering this concept, you have to keep the fact that degree of confined means number of dimensions inside nano. Degree of freedom means number of directions outside nano. There are so many problems related to the topics we have learned from the classification, and we can move on to some problems to memorize the concept what you learned by this discussion. And the first question, which is correct about 0-dimensional nanomaterials? These are the options to you. All dimensions are outside nano regime. All dimensions are inside nano regime. Only one dimension is outside nano regime. None of this. And you can arrive at the final answer. That is from your acquired knowledge. It is clear that all dimensions are inside nano regime. No dimension is outside nano. Hence the number 0. Now the next question. Which one of the following is an example of 1D nanomaterial? Here are the options in front of you. Thin films, quantum well, quantum wire and quantum dot. The question is about 1D nanomaterial, that is one dimension is outside nano. Hence, your answer is quantum wire. For quantum wire, the length is very high. You learned that aspect ratio is very high. So, 2 dimensions are nano, that is one dimension is outside nano. Hence, the name 1D nanomaterial. One more. Graphene sheet represents. Graphene, as the name indicates, it is a sheet. It is a sheet. Sheet means like a thin layer. What kind of material it is the question in front of you. The options are 0-dimensional, 2-dimensional nanomaterials, 1D nanomaterial, 3D nanomaterial. These are the options, and this about the right answer to you, that is 2D nanomaterial. That is for a sheet or thin layer or a thin film. 2 dimensions are outside nano, only its thickness, only 1 dimension is inside nano. Hence, the graphene sheet, nice example of 2D nanomaterial. and who introduced the classification of nanomaterial based on dimension. Absolutely, it is clear that Feynman is giving foundation stone. Sumio Ijima is a scientist who invented carbon nanotube. Eric Drexler used the term nanotechnology for the first time in its real sense, and the classification was introduced by R.W. Siegel. So, the right answer is R.W. Siegel, and that all about the presentation, that all about the module. Thank you.